We have already studied the theory of constraint optimization, and in particular we saw that the Karush-Kuntakar or KKT conditions are necessary for a local minimum of a constraint optimization problem, and the second order KKT conditions are sufficient under certain conditions. So, we make use of some of these ideas to devise algorithms for solving a constraint optimization problem. Now, we will be looking at some formulations, and in most of our discussion those formulations will be used to demonstrate the usefulness of some of the algorithms. So, let us assume that H is a symmetric positive definite matrix. So, one of the first formulations that we are going to study is a quadratic program with linear equality constraints. So, the program is of the form half of x transpose h x plus c transpose x to be minimized subject to the constraint that A I transpose x equal to B I, where I belongs to the set of equality constraints E. So, as I said that H is a symmetric positive definite matrix. So, in many occasions one comes across these quadratic programs, and there are simple ways to solve these problems. Now, I must mention here that there exist plenty of techniques to solve different constraint optimization problems, and it is very difficult to cover each and every technique in this course. So, we will select some of the techniques which are simple and easy to implement, and demonstrate their usefulness on some of the problems. Now, this is a simple quadratic program with linear equality constraint. Now, the ideas that we discussed here can be used to solve a quadratic program which has linear equality and inequality constraints. For example, the quadratic program with linear equality and inequality constraint could be of this form, where the script E and script I denote the equality and inequality constraint sets. So, the ideas we study here while studying the quadratic program with linear equality constraints will be useful in studying this problem formulation. Now, we then move on to the problem formulation where the objective function is not necessarily a quadratic function, but a general function f x, but the constraints are of the same type, the linear equality and inequality. You might recall that when we studied unconstrained optimization, we saw that Newton method can be used to solve unconstrained optimization problems by approximating a given function by a quadratic function at a current point. So, if we use similar ideas, then the given function, if it is twice continuously differentiable, can be approximated by a quadratic function at a current point, and then one can use these ideas to solve the problem with respect to that approximation, move on to the new point, and then again repeat the procedure. So, the ideas that we study here could be useful in studying the optimization of a general function subject to linear equality and inequality constraints. And finally, we will solve a general constraint optimization problem, or we will look at some of the algorithms for solving a general constraint optimization problem, where the objective is to minimize f x subject to some inequality constraints and some equality constraints, and note that these constraints need not be linear as was the case in the earlier formulation. So, this is going to be the outline of our discussion for the rest of the course. If the function f is convex, hjx is also convex and eix are affine, then this program will be a convex program, and there exists some efficient algorithms to solve convex programs. So, we will also see some of those methods. Now, there exist different optimization methods to solve these problem formulations, and some of them are mentioned here. So, some methods are Lagrange based methods, where they use Lagrangian function to solve a given problem. Some functions, some methods are based on penalty or barrier functions, and for convex programs there exist methods like cutting plane methods. Now, as I mentioned that there exists plenty of methods to solve constraint optimization problems, and it is very difficult to cover every method. So, we will study some of the prominent methods that would be useful in solving constraint optimization problems. So, let us look at some of the methods which are based on the Lagrangian of the given problem. So, let us consider the program quadratic program with linear constraints. So, the objective is to minimize half x transpose h x plus c transpose x, where h is a symmetric positive definite matrix and the constraints are linear equality constraints. So, A I transpose x equal to B I, and E denotes the script E denotes the set of index set of equality constraints. Now, we can write this program in a compact form by writing or by collecting the vectors A1 transpose, A2 transpose up to AM transpose into the rows of the matrix A. So, this matrix A will be a M by N matrix, where M is the cardinality of the set E, and the original program is just compactly written in this form. And let us assume that the rank of the matrix A is M, or A is a full row rank matrix. Now, how do we use the Lagrangian based ideas to solve this problem? Now, when we discussed KKT conditions, we saw that for a convex program where Slater's conditions are satisfied, the first order KKT conditions are necessary and sufficient. Now, you may see that since the objective function is convex, because H is a symmetric positive definite matrix, the Hessian matrix is positive definite. So, the objective function is convex, the constraints are affine, and we assume that Slater's condition holds. That means that there is at least one point in the interior, or the constraint set has non-empty interior. So, then the first order KKT conditions are necessary and sufficient. So, these conditions are obtained by writing the Lagrangian of this problem. So, the Lagrangian will be the objective function plus lambda transpose B minus Ax. Now, we intentionally use the multiplier lambda here, because in the course so far we have always used the Lagrangian multiplier corresponding to the equality constraint to be mu, but here we use lambda mainly because when we discuss about the quadratic programs with linear equality and inequality constraint, this notion of lambda will be useful. So, we continue using lambda for the equality constraint problem. So, if you write the Lagrangian of the given problem and take the gradient of that with respect to x, what we get is h x plus A transpose lambda plus c equal to 0, and it also should satisfy A x equal to b. So, these are the first order necessary and sufficient conditions. Remember that lambda is a multiplier associated with the equality constraints, and therefore, there are no sign restrictions on lambda. Now, these are n plus m equations in n plus m unknowns, and so which can be solved easily. But in particular, for this program, since H is a symmetric positive definite matrix, we can make use of that fact to write x in terms of lambda, and then get an explicit value for x in terms of H, C, A and B. So, let us see how to do that. So, we have these two equations, and H is a invertible symmetric positive definite matrix. So, x can be written as minus H inverse A transpose lambda plus C. Now, this x should satisfy A x equal to B. So, therefore, minus A H inverse A transpose lambda plus C equal to B. Now, we can use this and the fact that A is a full row rank matrix to find out the value of lambda. So, lambda will be nothing but minus A H inverse A transpose inverse into H inverse C plus B. So, we are able to get lambda in terms of A, H, C and B. Now, once we have that lambda, we can plug in that value of lambda here to get x. So, using this value of lambda, we get an expression for x, which is shown here. So, you will see that for a quadratic program with linear equality constraint of the form A x equal to b, the optimum value is x equal to this. So, it is very easy to find a solution of a quadratic program with linear equality constraint, provided the Hessian of the objective function is symmetric positive definite. So, that inversion of that matrix is possible. Let us see some examples which illustrate this. So, here is a problem to minimize this objective function subject to the constraint that x 1 plus x 2 equal to 1. So, in other words, we are interested in finding a circle of minimum radius which touches the line x 1 plus x 2 equal to 1, and the circle is centered at the point 3, 2, that is the x coordinate, x 1 coordinate of the circle is 3 and x 2 coordinate of the circle center is 2. So, here is a scenario where this is the point 3, 2, and we are interested in finding out a circle centered at this point whose radius is as minimum as possible and which should touch the line x 1 plus x 2 equal to 1. So, you will see that at this point on the x axis, x 1 axis, the circle touches the line x 1 plus x 2 equal to 1, and this point is 1 0, which is the solution to this problem. If we reduce the radius of the circle, then we will not maintain the feasibility. Similarly, if we increase the radius of the circle, the new point, there is a scope for the objective function to improve at the point where the circle intersects this line. So, this will be the only point where the objective function will be the least. Now, by writing down the Hessian of this objective function and writing this constraint in the form x equal to b, where A is a 1 by 2 matrix which contains both entries to be 1 and B is a 1 by 1 matrix with value 1, and if you use the formula that we saw earlier to find x, then you can verify that this is indeed the global minimum of the given problem. Now, let us see another example. Again, the circle with the center whose coordinates are 3 and 2 we want to determine a circle of minimum radius which touches the line x1 plus x2 equal to 4. Now, on the screen you will see the contours of circle, contours of the circle which having center 3, 2. This is the center of the circle, and you will see contours with different function values. So, you will see that this is the contour with objective function value 0.1, then this is the contour with objective function value 0.5, then 2, 4 and so on. So, as we move away from the center, the objective function value increases. For example, this is the circle with objective function value 8. Now, we are interested in finding out that circle which touches the line x1 plus x2 equal to 4 and the circle with minimum radius. So, this is the line x1 plus x2 equal to 4, and we are interested in finding out the point or the x1 and x2 pair where the circle touches this line and has the least function value, and this is the point which is the point where the function value is minimum and it also satisfies this, and this point is the point where x1 coordinate is 2.5 and the y1 x2 coordinate is 1.5. So, the solution to this problem is x1 equal to 2.5 and x2 equal to 1.5. Let us see another example. So, here the objective function has elliptical contours. The constraint set is still the same, x1 plus x2 equal to 4. So, let us see how the contours look like. So, the contours of the objective function look like this. So, this is the contour with the objective function value minus 28.5, and then as one moves away, the objective function value increases. Now, among all contours that are shown here, this is the contour of the objective function which touches the given line x1 plus x2 equal to 4. So, the corresponding function value is minus 28.5, and that objective function value is achieved using this point where x1 coordinate is 1.5 and x2 coordinate is 2.5. So, this point is the global minimum of this objective function. Note that the objective function is convex. So, in every local minimum is a global minimum. So, we can say that this is the global minimum of this objective function subject to this constraint, and the optimal objective function value is minus 28.5. So, these are some examples related to the constraint optimization problem, where the objective function is a convex quadratic function with positive definite Hessian matrix, and the constraints are linear equality constraints, and we saw a simple formula which could be used to solve such problems. Now, we move on to the second problem, where we want to solve a quadratic program with linear equality and inequality constraint. So, in particular, for a given H matrix which is a symmetric and positive definite matrix, the aim is to minimize half x transpose h x plus c transpose x subject to A transpose x equal to B I belongs to the index set of equality constraints, and A I transpose x less than or equal to B I, where the index set comes from the script I. Okay. So, now we have a set of inequality constraints added to the problem. Now, how do we solve this problem? That is our next question. Now, to solve this problem, we require the concept of active sets, and when we discussed about unconstrained optimization, when we discussed about constraint optimization theory, we saw the concept of active sets. So, suppose this set is a feasible set or the constraint set shown by the shaded region, and if we consider a point x1, now you will see that only one constraint is active at this point. The other 4 constraints here are inactive. Inactive means that the corresponding constraint is satisfied with inequality, and this is the only constraint which is satisfied with equality. On the other hand, suppose we take this point, you will see that this constraint and this constraint, they are active. So, at this point the constraints which intersect at this point are active. So, at a point there could be multiple number of constraints which could be active. Now, if we take a point which is here, let us call this as x3 and this point was x2. So, you will see that at this point none of the constraints is active. This point is in the interior of the feasible region and none of the constraints are active, because all the constraints are satisfied at this point with strict inequality. So, this idea of active sets is used in solving the quadratic programs with linear equality and inequality constraints, and the resulting method is called active set method. Now, let us look at how this active set algorithm works. Now, given a feasible point, what one needs to do is that one needs to find out all the constraints which are active at a current point. Now, all the constraints which are equality constraints are definitely active at a current point. Now, in addition to those equality constraints, one has to check whether some of the inequality constraints are also active, and all such constraints put together form an active set, or also called a working set at a given point xk. So, if you are given xk, a feasible point at the kth iteration of the algorithm, then the working set associated with xk will be denoted by wk, and it is defined as the set of all equality constraints and the set of all inequality constraints which are satisfied with equality. So, we collect all inequality constraints and find out which constraints are satisfied with equality as far as current point is concerned. So, AI transpose, this should be xk, that should be equal to bi. So, if the current point satisfies some of the inequality constraints with equality, those are combined along with the equality constraints to find out wk, and that is going to be the working set at the iteration k. So, at every iteration the working set varies, and the constraints which differ are the inequality constraints. The equality constraints are common for every feasible xk. So, once we find out the working set, then the idea is to solve the quadratic program with respect to the working set, and since the working set is the set of all equalities, then we can use some of the ideas that we studied when we studied the optimization of a quadratic program with respect to linear equality constraints. So, once we find the working set wk, the next step is to find the descent direction tk with respect to wk. Now, that direction can be found by solving another quadratic program. So, we have minimize half of x transpose h x plus c transpose x subject to a so AWK denotes the active constraints associated with the working set WK. Now, with the current point xk, we are interested in finding the direction d. So, what we have is what we want to find out is xk plus d, such that any movement along the direction d, at least a small movement along the direction d should be feasible. So, we rewrite this problem as minimize half of xk plus d transpose h xk plus d plus c transpose xk plus d subject to a wk xk plus d equal to b. Now, this is the optimization problem with respect to d. Xk is constant. So, if we take out the constant terms from away from this objective function, what will be left with is half d transpose h d plus c transpose d plus hxk transpose d. Now, hxk transpose d plus c transpose d is combined to write that function in terms of the gradient, because the gradient of this function is hx plus c. So, gradient at xk is hxk plus c. So, the objective function becomes half d transpose h d plus gk transpose d. Now, subject to awk d equal to 0, because awk x is always b and it is true at xk. So, once you find the descent direction dk, we find out the step size and such that xk plus 1 is also feasible. So, as I mentioned that given a feasible point xk and wk, the associated program that we would like to solve with respect to the working set W is to find dk by solving this problem, where half of d transpose h d plus gk transpose d is minimized such that ai transpose d equal to 0, where I belongs to the working set. So, the direction d is found by solving this problem, and then the next step will be to get a step length and make a progress towards xk plus 1, so that the objective function is minimized, and this procedure will be repeated till one reaches an optimal point. Now, we will see more details about this in the next class. Thank you.